Thank you, guys. Thank you for inviting me here. I'm very excited to be here. So I'll be talking about large-scale machine learning for about an hour, I guess, and then I want to cover a topic that is related, but not necessarily parallel machine learning. To me, it's a very exciting topic, actually, if we have time for it. So the actual reason why I'm here is this one. Very proud of publishing a book of Cambridge University Press. I'm not the author of that book. I'm the editor of this book, and actually co-editor. The other editors are Misha Bilenko from Microsoft Research and John Langford from Yahoo Research. So I'm not the author because there is no one single person in this world who actually knows all this material. It's very emerging. So we cover pretty much anything that is available at least has been available. Probably there is something new that is not covered in the book. The book was actually printed in January. So since January, things might have changed. But it's a very emerging topic, admittedly. So we cover many platforms on which you actually can run large-scale machine learning, different algorithms, how to parallelize SVMs, how to parallelize boosted decision trees. We cover non-standard supervised or unsupervised learning. So we covered, say, semi-supervised learning and transfer learning and online learning. And we show a few very interesting applications in machine vision and speech recognition. And those are contributors of the chapters. As you can see, we made our very best to cover the top researchers in the area. So it's kind of hard to find a strong group that is actually not on that list. This book covers a gap of more than 10 years since last books were published on the topic. And within these 10 years, many things actually have happened. So one of the most important examples is that the size of the data. Right? I can show you just one example based on my own personal experience, just to start with something personal. So 10 years ago, and actually 11 years ago, we published this paper at SIG-IR, which was on text classification, but one of the ideas in the paper was that, there is this data set called Reuters. It has 10,000 data instances. You know what, guys, don't use it. It's kind of too small, too simplistic. That was one of the ideas. And in 2008, we actually published a paper on clustering a collection of almost a million documents. And you know what? Back then, we found only one prior work that did the same thing. And last year, we published a paper on classification of 100 million data instances that we have on LinkedIn. And if we plot this graph, that's pretty much how it looks like. So it's basically, if it's not super linear on a log scale, you know what, guys, it actually kind of looks scary. It is. So we need to think what's next, right? Other things that have changed within these 10 years, world has gone mobile, right? So like pretty much everyone has a cell phone now, and all those cell phones produce a lot of data. Social networks are online. That's what we didn't have 10 years ago either, and it's a lot of data too. And another thing that is very important for machine learning, now we have this tool that is called crowdsourcing, right? I guess that many of you are familiar with Mechanical Turk, SummaSource, and other services. I'll be talking about that in this talk for sure. My main takeaway from the first part of this talk is that, you know what, we need to build tools that the data size is basically the main input. So we need to build separate different types of tools for different sizes of the data. And let's talk about the very simple one, right? 1,000 data instances. You know what? If you have 1,000 data instances, give them to me. I'll label them manually for you within like 3 days. So what I'm trying to say is that it's just not enough data to even do machine learning, and we definitely shouldn't publish papers on like results on the data sets like that. So once in a while you have like, if every data set on this list is like, a terabyte of data, then it's a separate topic. But usually when you talk about a data instance, it's something relatively small. So once we are talking about 1 million of data instances, that's a different story. That's actually the hottest area right now. That's what we usually process nowadays with machine learning methods. So 2 aspects. One is you actually can label or process all the data manually using crowdsourcing. And another aspect is that 1 million data instances is actually not a huge number. You actually can run pretty heavy algorithms on data sets of that size if you parallelize. I'll be talking about that too. Another interesting angle that we can look at data sets of this size. You know what? Once you have 1 million data instances, you will definitely find similar things within this data. You will find kind of classes or clusters, whatever. It cannot be totally scattered around. I'll just show you an example. But it definitely can be too homogeneous. That's certainly the case. And before you work with data sets of that size, you actually really need to understand what you have in your data. You need to probe the data. You need to pre-process the data. Otherwise, it just won't work. So what I mean by big data sets cannot be too sparse. Say we have 1 million documents. And by the way, many of my examples will be in the text domain because I'm mostly a text mining guy. So you want to cluster or categorize them by topics. You will not have 1 million topics, will you? Because it's just not practical, right? But there is another aspect of that. So I did a small experiment. So I built 1 million documents randomly, but I sampled them from the real language model, real distribution of words in the language. And what I have is that for every document on this list, you have, on average, 245 similar documents. So even if you totally randomly sample from the language, you will have things that are similar to each other just because the language doesn't allow you to have a huge variety. In real world, the data sets, they definitely are denser than this random one. So we need to remember that we will have things that are similar to each other. But look at another aspect. Can our data be kind of too dense? So look, let's say that we have like, 1 million images. And I'm just giving you a snippet of like 10 of them. You know what, guys, like some people will ask questions ahead of time, and some will just jump and run a machine learning algorithm on a data set that looks like that. And I'm like, those just file names, right? And your data can actually look something like that. So what I'm trying to say, like 70% of that data set actually can be duplicates. You need to know that before you start doing anything, because so actually you need to work with like pretty much 30% of that data, right? And that data of 30% in size has different characteristics from the original data set that you had in hand. And here I'm giving a real world example actually. So in 2003, I was probably the first, I think I was the first data miner who put my hands on this Enron email data set. I think that some of you heard about that data set. it's a big data set, right? About 1 million data instances or something like that. And I started running some tests on the data just to understand whatever I have on this data. And one of these tests that I actually did, I tried to build this timeline of these email messages that were sent, like to see how they're distributed over time. And out of the sudden, I've seen strange things. So many messages were sent on exactly the same millisecond. I'm like, huh. It looks strange. And it happens over and over and over again. I'm like, it cannot be true. So what turned out is that 40% of that data were actually duplicates. I guess it was just a pre-processing mistake or something like that. Once we removed 40% of the data, you know what? It out of the sudden started looking totally different. All my statistics that I were running produced some totally different results. So we need to be careful about working with big data. So the data will have, in many cases, data will have duplicates. And let me show just one example how you can deal with duplicates. It's just my personal take again, like it's just one example. Let's say that every squares here are data instances. And you want to find similar, like pretty much near duplicates to remove them from the data. How would you do that? It's like, think about like a 1 million data instances collection. Let's say that we just cluster this data set with your favorite clustering algorithm. And you know what? You can cluster the same data set again with a different algorithm or a different random seed or something like that. And you can do it again and again and again. And you know what? Then you kind of merge those data, you kind of map them onto each other. And out of the sudden, you see data instances that always go together. No matter which clustering algorithm you apply, this data instance and this data instance are always together in one cluster. And you're like, huh, probably they are similar to each other. So that's one of the approaches how to deal with near duplicates. Let's talk about a data set of a larger scale. Let's say we have 1 billion data instances. That's the web scale. That's something that is kind of difficult to deal with, right? So first of all, it's obvious that you will have data in various formats. Like it can be video and pictures and whatever. And you will have duplicates or near duplicates. So like to understand how many of them you have is by itself a difficult problem that you will have to deal. And the data will be badly pre-processed. So like investing a lot of time in pre-processing and even actually thinking about how to store this data is already something that needs to be on your agenda before you start working with data sets of that size. And once we move up to trillion data instances, that's becoming like a border case. We don't really know how to deal with trillion data instances. Probably some of you can do that. I definitely think that it's too much. So what happens is that you even cannot own the entire data set. It will be like different entities, different organizations that will own different portions of this data set that they will not want to, basically make public or something like that. So all issues related to inconsistencies and skewness and privacy are very important. And even to sample from that data set is already not really trivial. Let me show you one example that I took from chapter 16 on the book, how to deal with data sets of that size if we have this privacy issue. So we have, say, n entities. Every entity owns a portion of that data set. What we can do is we can say, why don't these entities share a small portion of whatever they have? So we'll have this part of the data set that will be common for every entity. And now what we can do is like each entity, each machine learns its own model, and then they synchronize their models over this mutual component. So that would be an approach to deal with data sets of the size of trillions of data instances. And by the way, we have an example of a system like that, definitely not on trillions of data instances, but it's still, like a proof of concept. We have it in the domain of a recommendation system. OK, we've talked about the data. What do we do with the data? I guess we learn a model, right? So which type of model do you learn? Supervised, unsupervised? To machine learning people in the room, it's kind of obvious, right? It's depending on the task. Not only. So it also depends on how much label data do you have. If you have enough label data, you know what, guys, just learn a classifier and you will be all set. And also another issue that is important, do you actually trust your labels? That's another question when we are talking about large-scale machine learning. That's a very valid question to ask. Let me talk about the size of the training data first. So I'll give you just 2 examples, and we will compare them. Let's say that we have 1,000 labeled data instances, 1 million unlabeled data instances. Another example, 1 million labeled instances, 1 billion unlabeled instances. In both cases, the ratio between labeled and unlabeled data is the same, and it's actually very low, right? So do you want to learn a classifier in the first case, in the second case, or both? What I'm trying to say here is that it's a bad idea to learn a classifier on 1,000 data instances and apply it to 1 million. So it will be too sparse. It might not even cover, big chunks of, like many, I would say, specific effects that you would see in the unlabeled data might not be covered at all in your labeled data. Versus in the second case, it's a different story. I hope that I convinced you already that once we have a billion data collection, we'll have a lot of duplicates, we'll have a lot of stuff that would make this problem kind of more like denser than you would imagine. So if we build the right data set of 1 million labeled instances, we actually can tackle a billion. At least that's my personal take from that. Another aspect that we definitely need to take into account, I already mentioned it, is do you trust your data actually? So most of your labeled data comes from users. And you have at least 2 ways to collect label data from users. One is just to go to user and ask the user, do you like it, you don't like it? Something like that. Another aspect is just you watch whatever the user is doing, and you try to infer the user's behavior from whatever you are watching, kind of an implicit feedback. Think about click-through in web search or something like that. And once you have the huge data, it's actually not obvious whether the label data that you have is actually representative with respect to a lot of unlabeled data that you have or might have. So what I'm trying to say is, once you have explicit feedback, once you ask people, do that for me, label those instances or something like that, you need to be really, really careful, because people who do that for you, it's not the general population. They might have some special incentives to actually go ahead and do those clicks for you. Here's one example. So let's say that our task is to find like high quality, important people on LinkedIn, like, very highly professional people. And we can just have one simple idea. Why don't we use recommendations on LinkedIn profiles? Whoever have recommendations, we can say those are, the most important people or something like that. So that's the explicit feedback. People give recommendations to others, right? Here's one example why I actually think that it might be a bad idea. So the quality of the text is not perfect, but I'll tell you what I have. So this is a recommendation, actually like 2 lines of recommendation that was given to Sarah Palin in 2008. So I actually don't doubt that the person who gave this recommendation was very open-hearted, and she actually really adores Sarah Palin. But here's one aspect. Sarah Palin's profile is one of the most visible profiles on LinkedIn. Whoever gives a recommendation to Sarah Palin becomes enormously visible. So does this lady have an incentive to actually provide a recommendation to Sarah Palin? I think she does, and we need to take those things into account if we actually want to learn a supervised model on data that comes from explicit feedback. So what do we do if we don't have enough good labeled data? We can take two approaches. One is, instead of building a classifier, kind of dictating our model based on our labeled data, we can take this labeled data as a type of a guidance, kind of you skew your unsupervised model with a little bit of labeled data that you have in hand. I'll talk about that in the next slide. And another approach, just label more data, a very simple one. Since we have crowdsourcing, we actually can do it now. So how would you use a little bit of labeled data to actually improve the results of a system with a lot of unlabeled data? So it's just, again, one of the examples that we were working on. There are many of them. But this example is like that. Say we want to categorize documents, and we have just a little bit of documents that we call D star that have labels. And what we do is like that. We actually cluster the entire data collection, build a clustering D tilde, while maximizing the mutual information between the clustering we are building and a kind of a natural clustering of our label data where every class is like a natural cluster. So that's one of the approaches. And you know what? In some cases, it actually works better than classification. Basically, we can build a classifier based on D star and apply it to D, and it might produce worse results than using an approach like that in a semi-supervised clustering fashion. So I have a little bit of details of how to do that. I guess I can skip it, but the slides will be available. So the second approach is just label more data. How would we do that? It sounds very simple, right? You create like a million data instances, send it to Mechanical Turk. Tomorrow you have them labeled. Not at all. So I guess that many of you in the audience actually are familiar with how Mechanical Turks work. But for those who are not, I'll explain what I mean, because it's actually pretty important. So any worker who can game the system will game the system. And we need to prevent them from doing that. How do we do that? We first need to introduce some type of validation framework to their work and use qualification tests to filter out, like smart people from the rest. And actually, if you want to do that, it will cost you quite a lot of money. It's not that cheap. We know that workers will work for 1 cent a click. But if you want a very high quality label data set, it will be more expensive. So how to label 1 million data collection? So first of all, you budget time, and quite a lot of time, say like a month of work. It's not that much actually. And you budget money. So here I'm putting on the table $50,000. So for people in academia, it's actually quite a lot of money. But for companies like LinkedIn, it's OK. We can deal with that. And I'm pretty sure that many of you actually can deal with data sets of that size. So how to label this data? First, you actually hire a friend, someone who you know, someone you trust. This guy will be labeling data for you, sitting next to you. You will just check whatever this guy will be doing, and you offer the guy a lot of money for this work, because the guy wants to be incentivized to actually do the stupid click, click, click work. It is stupid, but think about all your business model is based on the fact that you have a lot of good labeled data, right? But you actually don't, right? So it's very important for you. It's not important for the guy, right? And then you hire, say, 100 mechanical workers. And how you hire them, you actually create some type of qualification test that will choose like the right people for this test, for this task. And you need to work with them kind of personally. You need to know them. They actually really like it. And you educate everyone about this task. You need to spend time on that, and then you offer them a lot of money. So 4 cents per click is actually a lot of money for, especially for people who, like, many mechanical turks are based in India. 4 cents per 1 click, it's not a small amount of money at all. And then what you do is like that. You ask your friend to label 500 data instances a day, something like that. It's tedious, but it's doable. I did it myself. It's doable. And you spot check this guy's results. So you need to make sure that whatever this guy is doing is high quality, because you will be using this guy's results to validate the results that 100 mechanical workers will be doing. And you give every worker 1,000 instances per day. That's actually not a big number. Some of them can produce 5,000 a day. I don't know how to do that. And I seriously doubt the quality of the results if they do 5,000 clicks a day. And for every worker, you will use a little bit of the data that your friend produces as a validation set. Every time that you grab the results from mechanical workers, you just use the script that compares whatever they are doing on that validation set with the results that your friend produced. And if they didn't do a good job, out. You always can bring more people. So some of those workers actually complained totally. So I was receiving those messages, how could you fire me? I need to support my family. And I had tears in my eyes, but I'm like, you're producing garbage. So like, is it worse? So I need high quality label data. That's what I need. That's the only thing that I need. And you just let it work for like 20 days, and everyone's happy. Hopefully. OK, now we have a lot of training data. What do we do? Go and train your model, right? 2 rules of thumb. The heavier algorithm you're building, the better the results are. Use quadratic algorithms if possible. Do parallelization. Another one. Don't use super quadratic algorithms. Cubic algorithms, forget about them. Anything that you learned in like your computer science classes at school, not anything, but many topics are talking about like cubic algorithms, and up doesn't work. And parallelization is an important part. So it's essentially what I'm trying to talk about here. This talk is the parallelization. Let's see what are the platforms that we can use for parallelization. So I'm coming from like the very general framework of peer-to-peer networks that actually can parallelize things like unbelievable. But it's not robust. I'll just show you how it works. And I kind of go down to like very specific systems that implement machine learning in hardware. And those systems cannot process a lot of data, but they can work at the speed of like nanoseconds. And my example will be k-means. I'm sorry to be that boring, but like I'll just, as a running example, I guess it will be fine. So for those who don't know what k-means is basically it has each iteration it has 2 steps. One is, so we first need to choose like centers of every cluster. At the first step, E-step, we associate every data point with the center. And the second step, we recompute the centers. So here's like I even have like a visual example of that. So first we choose those centroids, and then we associate data points with the closest centroid. And then we recompute the centroids to be the center of mass of your cluster. And then you recompute the association again, move the centers, recompute, end up with beautiful clusters. You know what? K-means is actually quite a bad clustering algorithm. And I can tell you that, like, from my personal experience, I've been doing clustering for 10 years. But it's just an easy algorithm, right? So like, I'll be using it as an example. So how do we parallelize K-means? Very simple, right? So again, first find some centroids. And then actually what you can do, you can split the data. Let's say that you split the data uniformly at random to, say, 2 machines here. And you run an iteration of K-means locally. You associate data points with centroids. And then you move local centroids. And you send them back, merge them together. And then send them again to your machines and do it like that. So let's see what we can do with peer-to-peer systems on the example of K-means. So peer-to-peer systems, think about the internet, right? You have like millions of machines somehow connected with each other such that each machine sees only its neighbors. And each machine can store a lot of data. So it's actually practically unlimited in scale. So theoretically, at least, you can work with, like, trillions of data instances pretty easily. But we have many problems, right? Machines will fail. Communication is a bottleneck by itself. If you want to aggregate information from all the machines together, it will be very expensive. But what would be kind of much cheaper is the broadcast, if one machine wants to talk to many. And messages are usually sent on a spanning tree over this network, where the root of this tree is kind of chosen arbitrary, where all the messages kind of converges, that's the root, something like that. So how do we do K-means in a peer-to-peer system? The important part here is to sample. We actually cannot work with all the data kind of simultaneously. First, we need to sample centroids, initial values, initial centroids from the data set that we have. And to sample them uniformly at random, it by itself is a big trouble in a peer-to-peer system. So there is a special algorithm that Data et al. Proposed that does this. So once we have those centroids, we broadcast them to all the machines and run K-means locally on all the machines separately. And then we need to aggregate new centroids, right? So what we do, we actually sample, again, machines. Right now we're sampling machines and aggregate centroids only from those machines. And then again, you broadcast those centroids to all those machines. Let's go down this stack towards some more specific systems. So let's talk about virtual clusters, which is more like data centers. I'm pretty sure that many of you are familiar with this setup. So I'm talking about like hundreds of thousands of machines which run some type of, have some type of distributed file system that takes care of redundancy. And fault tolerance is definitely a big issue, so it's more like cloud computing paradigm here. So because machines, once you have that many machines, they will die eventually, even pretty often. That's what Google say, right? If they have a data center of 100,000 machines, they die at the speed of like one a second or something like that. So MapReduce is actually the main paradigm how to deal with distributed data in a data center, and I'm pretty sure that every one of you are familiar with MapReduce. But anyhow, like just for people who might not know, I want to cover it to be on the same plate. So a MapReduce system is basically you split the data to portions, you run an algorithm on each portion, then you reshuffle the data and run a second part of that algorithm. So the first part is called mapper, second one is called reducer. and a mapper produces key value pairs, and the data is sent to reducers based on the key value. So just as, again, a simple example how you count words in using MapReduce. So let's say that we have 1 billion documents distributed like in a distributed file system. You need to count how many words, global counts of words in this data set. So the data is sitting in the distributed file system. A mapper just takes every portion of this data and computes local counts over this data, produces word count pairs where the word is the key, and the data is being sent to reducers such that all the keys are together, all the local counts of words are together, and you aggregate them into the global count. How do you do k-means on this data? Also very simple. And we have it in Chapter 2. Chapter 2 is actually a fairly introductory chapter in the paper. So first of all, mappers need to read their portions of the data in the memory, and then assign, and also they read the centroids. Let's say that we have initialized them somehow, and then they assign data instances to centroids, recompute local cluster centroids, new centroids locally, and also recompute this size, local size of clusters, and then reduce this data. Those statistics are being sent to reducers. They aggregate local centroids weighted by the size of the clusters, and they build global centroids. And what they do, they actually write those centroids to the disk. And mappers start over. What is kind of obvious what the problem is, right? So at every iteration, a mapper actually needs to read the data into the memory, and its disk access is basically the bottleneck. What's funny about MapReduce? So we've been talking about MapReduce for quite a few years, right? For some people, it's just too low level. They, analysts used to work with SQL, and they want to work with SQL, right? Even with the very big data. And for some people, some engineers, MapReduce is just too high level. So they want to know exactly what they're doing with their data. And I can give you just, I've just given you this so simple example of counting words. And you definitely know that words are distributed as a power law in a language, right? So if you just use, run this algorithm blindly, what you will end up is you will have many machines that will just count, do their work very fast, and you will have a few machines that will be stuck because they will be processing a lot of counts from words like the, from, at, and things like that. So I am oversimplifying things dramatically here. But what I'm trying to say that it's not obvious whether MapReduce is the right paradigm at all. So what people have proposed is to build those different types of wrappers around MapReduce. Some of them are not really stable, but some of them are actually good. And here at LinkedIn, we are using Apache Pig, a funny name, but a very strong system, and a pretty simple system, actually, that was proposed at Yahoo Research a few years ago. And at Microsoft, our friends here down the road are using and developing, actually, what's called Dryad-Link. It's a C# language, and it's actually very powerful. I'll just show you an example. So how do you do k-means in Apache Pig? Let's say, so it's an SQL type of language, if you think about that. So basically, your input should be tables. Let's say that we have two tables, like the data and the centroids. And tables are very simple, right? So like it's a document ID, word count, document ID, word count. And your centroids actually will be stored in exactly the same format. Here's the code. It's a working code that runs k-means clustering. So that's the first part of the code, the part where associates data instances with centroids. Guess I'll need a little bit of water here. So how do we associate documents with centroids? It's like it was a document domain. So we just compute cosine similarity, for example. I'll just walk you through the code just to see how would you approach a problem like that. You don't, it's like just an example, right? So first you compute this products of counts, comes over here, and then you compute the actual dot product between your document and the centroid. I'm using the sum function here. Then the denominator comes from here, from the square root. And then the ratio is over here. And then finally the argmax. Actually, we are very lucky to have the top function in Pig that does it for us. And you know what? Do you see the problem? So every time that you run join or group, you actually need to run MapReduce. So for the first portion of one iteration of MapReduce, you need to run one iteration of k-means, you need to run 5 MapReduces. I'm pretty sure that this code can be optimized, but I'm pretty sure that it cannot be optimized that dramatically. For the second portion, you actually run 4 MapReduces. So it's 9 MapReduces per one iteration of k-means. You know what, guys? I actually ran this algorithm, and I was so happy that I actually can cluster a big data set, but it took me a few hours. So you can have some optimization, and Pandey et al. Proposed at least one optimization to increase the speed. What they were saying is that you run MapReduce one after another, and MapReduce takes time to set up, and then you process the data finally, and then you tear down. So this is one MapReduce, this is another MapReduce, this is third MapReduce, etc. But the data actually moves from a process to a process, right? So what they proposed is like that. Why don't we start initializing the next MapReduce procedure before you ended up running the previous MapReduce procedure? Worked for them, and at least the speed was improved pretty dramatically. So how do we do k-means and dryadling? So the beauty here is that it's such a nice language that actually k-means is literally 2 lines of code. And this is the E step of k-means. You actually need to write like a very simple procedure to compute nearest centroids per data instance. But to aggregate the centroids is just literally 1 line. So the language is beautiful. It's very powerful. And by the way, that's the execution plan of this k-means algorithm. You see, we kind of find some similarity here to whatever we have just seen, right? Those are pretty much MapReduces that are ran one after another. And what's the beauty here is that you definitely don't need to read the data and write the data to the disk, so everything is already implemented for you. So what are takeaways from here? First, machine learning in Pig or SQL is, well, it's kind of awkward. Not very straightforward, let's put it like that. But dryadling actually can do machine learning pretty well. And by the way, guys, like in the book, the authors of that chapter talk about how to do that for Kinect. And I was absolutely thrilled to see how it works. It's very impressive. And the news for, well, I guess it's not a news for many of you, but probably for some, is that machine learning becomes systems. Once we run machine learning on a lot of data, we actually really need to understand how the system works from inside. So let's go down the stack to a smaller system, high-performance computing clusters, supercomputers. Think about something like that. Usually have like, you can have thousands of cores in one pretty big box. And there are zillions of architectures. I was working with HP cluster like that. It's really impressive how fast it is. And what's interesting and nice, actually, that fault tolerance is not a big deal. Cores would not die that often on a machine that is well, well designed, actually. I'm not saying that it won't happen, but it's just not something that you really need to take into account once you run a machine learning method. And the most typical protocol to communication protocol will be MPI, Message Passing Interface. It was proposed 20 years ago and still useful. So it's a very simple system. Think about processes that you run on your hardware that just send messages to each other. You use like bsend to send a message from one process to another. And then you use receive function that will wait until this message arrives, and then it continues processing whatever it was doing. You also can broadcast messages, and you can have a barrier. Once you have it in your code, all your processes will stall until all of them are done. This way, you synchronize all of them. So MapReduce is very generic and very powerful. So you literally can mimic, or what did I say? MapReduce. No, I meant MPI, right? So MPI is powerful, and you can mimic MapReduce with MPI. The difference between an iterative application of MapReduce with MPI is that the disk is a problem. There is a disconnect here, right? You need to write to the disk and read from the disk again. With MPI, you don't have to do that at all. And the most usual paradigm is actually a master-slave. So you have one master that controls many slaves that do the processing for you. How do you k-means on MPI? Pretty simple too. So slaves first read their data portions, and they will never need to reread them again. Master broadcasts the centroids to slaves. Slaves do their local MapReduce, recompute their local centroids, send them back to the master. Master aggregates all of them and broadcasts them again. So it's very similar to whatever we were seeing with MapReduce, with one difference that you don't need to read from the disk and write to the disk. MPI is very powerful. So one aspect that I have just mentioned, that you don't need to reread the data and even parameters. You can store them locally. Another very interesting aspect that was proposed in chapter 4 in the book is that you actually can kind of construct a hierarchy of master slaves on the fly. Once one slave kind of thinks that it has too much data to process, it can become a master and create more slaves that process this data for you. A very powerful method. So takeaways on MPI. It's a very old system. It's very well debugged. You just basically won't have a bug in MPI. Very flexible and very well suitable for iterative processing. Not fault tolerant at all. So you need to implement your own fault tolerance on top of MPI, which is usually not the case, especially with like supercomputers as HPs, for example, but you need to have at least something in place. And unfortunately, it's not very popular any longer. So if you have a typical Hadoop cluster, you might not have MPI, which is kind of a little bit sad. So let's go down the stack even more to multi-core systems. Multi-cores is like kind of obvious. You guys are familiar with them, definitely. So it's like one machine. It has like dozens of cores. Nowadays, you can have 64 or something like that. You have shared memory, and multi-threading is the way to parallelize things on multi-core. So the first question that you're asking when you need to parallelize using a multi-core system is basically, does your data fit the RAM? If it does, that's great. If it does not, then you will use some type of streaming, and disk access will be a big bottleneck here. But even if it does fit RAM, still the bus between your CPUs and RAM would be a bottleneck. So you need to write and read in small portions and kind of scattered over time. And chapter 20 is actually talking about something like that. So we can do machine learning on GPUs. That's an interesting topic, actually. I think that you guys know what GPU is, but for those who don't, every laptop that you have has a GPU unit, graphics processing unit, that kind of, helps to show this nice picture on the screen. But in it, this unit is very well parallelized. And what NVIDIA has done, it let you use this parallelization unit to do, like, very heavy processing. So your laptop actually can run, a lot of data in a fraction of time if you want to use GPUs. So a GPU, it consists of hundreds of multiprocessors. And why it's called multiprocessor? Because each multiprocessor has a few ALUs inside. Each ALU runs the same line of code, actually, in parallel. So if you have a lot of branches in your code, like if then else's, that's not good, because then like only portion of your multiprocessors will work and the others will be stalled. How do you do machine learning on GPUs? First, you ask a question like, what you're optimizing for. Because if you want to use GPUs, you actually need to feed all the data in the memory. So usually what you're optimizing for is speed, not the size of the data. It's very good for real-time tasks. And a typical case, I'm not saying you always do that, but a typical case would be to learn the model offline using data centers or whatever. And if you need to apply this model really, really fast, then we would use parallelization on GPUs. And we have two examples of that, those tasks. One is for machine vision, another for speech recognition, in chapters 18 and 21 in the book. And by the way, Jiki Chong and his colleagues in chapter 21 used GPUs for speech recognition. And what they managed to do is they managed to do speech recognition at the time that is above real time, meaning quicker than people talk. And well, I'm not a very quick speaker, but anyhow, like they can do it faster. And that's actually, that's a big deal. And it turns out to be very useful. How do we do k-means on GPUs? First, the association step, when you associate data instances with clusters, centroids, you do that on GPUs because that's highly parallelizable. So every multiprocessor processes one data instance, and every ALU works with one feature in parallel. So like within one shot, you actually can do the association really, really fast. And then you recompute the centroids on the CPU level, just because you don't have to have a lot of parallelization here. It works well for dense data. If your data is too sparse, then many of your ALUs will be stalled. So it's not a very good idea. And what is important is how you actually transfer the data over the bus between the GPUs and, I guess, CPU. So you need to avoid those like chunks of data transferring. You need to distribute it over time to actually utilize this bus in the best fashion. And what you also can do, once your GPU is processing the data, you can transfer the next data instance to be stored in a local memory of the GPU. And if you do that, guys, the speed is unbelievable. 4 million data instances clustered in 9 seconds. And let's talk about the last system on my list, which is FPGAs. FPGAs are actually hardware units, parallel hardware units that are designed specifically for a particular task. So you can implement machine learning in hardware. So you use a hardware description language actually to program them. And you can use this to actually speed up training and inference. And we have 2 chapters about that, Chapter 7 and Chapter 19 in the book. And in Chapter 7, they propose, like Durdanovich et al. Propose a very interesting system that actually does hybrid parallelization. First, at the level of multi-core, and then they use FPGAs to very fine-grained parallelization. So I've covered 6 platforms so far, and I'm pretty sure that more platforms are available. How do you choose the platform? Obviously, the first question is how much data do you have? If you have not much data, say gigabytes, which will feed the RAM, you know what? You really don't need to use data sensors for a data set of that size, because it will be just a hassle even to transfer this data, right? Another important question is, are you optimizing for speed or not? Do you need this real-timeness? If you do, then you need to parallelize at a very low level of GPUs, FPGAs, and etc. Another question is, do you parallelize your training process, or you parallelize your like application of a trained model? That's another important question to ask. And in many cases, it's good enough to train the model offline. If you optimize for speed, you then parallelize the application step. So I've covered the first portion of my talk. I don't know how much time I still have. I want to talk about something kind of exciting. At least I'm totally excited about it. If you guys have 10 minutes, let's jump into it. So yeah.
Can I hear something exciting?
Sure, wonderful. Thank you. And by the way, this link has the slides, and it actually has 3 portions of slides. Misha Bilenko is covering all the interesting parallelizations of heavy algorithms such that boosted decision trees. So if you want to hear more details about how to actually parallelize machine learning algorithms, that is covered in Misha Bilenko's part. And John Langford is talking about parallelization that goes to extremes. A very interesting application, and he's actually using it at Yahoo Research. So let me talk about something very similar, but not necessarily parallel. So I'm trying to talk about a system that would kind of bring to some extreme of our abilities to process the data. I presented it at KDD last year. So I'm trying to be funny here. I hope that I am actually funny. I'm not sure. So recalled 1990. Well, I was a teenager at that point. Could we imagine that by 2000, everyone will have a device in their pockets? I don't think so. Now think about 2000. Could you imagine that everyone will have a GPS in their pocket or in their car? So by 2010. I don't think so, but I actually did predict it. You can't look at my website of 12 years ago, so I'm talking about something like that. And you know what? If I did it now, I think that I can make a prediction. So by 2020, what I'm predicting is that this device will be recording audio or probably even video 24/7 and sending this audio to your private local locker on the cloud. So why? First, it's personal security. Every theft, every person who has something malicious in their mind will know that the guy will be recorded. So it's an important thing. And another one is it's a perfect memory. Think about your first kiss. It will be here. And you actually, when you recall it, it's like it's your perspective of 20 years ago. But you actually can kind of grab that moment. And now let's say, I agree that it's creepy. But the notion of privacy is actually kind of moving nowadays. And if you think about the ability of actually, slicing and dicing this data. Not only on the level of one individual, because that will be totally creepy. But let's say that we have chunks of the data of the size of 1 million human beings. That's good enough, right? So we actually can slice it. Think about like a question: what exactly people in Syria are talking about right now? That's a fascinating question, because there is one journalist who's just sitting somewhere in Damascus and reporting what exactly is going on. That's one person with one perspective. We actually can have a picture that is actually pretty objective. It's possible. It's changing your kind of notion of objectivity. It's possible. I hope that it will be possible. But let's see how much data we actually have here. So let's say that we are recording all this audio all the time. You know what? In 3 years, we end up with a zettabyte of data. You know what zettabyte is? I don't know either. But it's a lot of data, so it's like something that we are not used to in any way. But let's make a simplification here. Let's say that actually speech recognition works, and with applications like Siri or something like that, we can say that it actually might work in like 8 years from now. And let's say that we store only the text, not the audio, but we can store the text, the audio, but we will process the text. So we'll end up with about 100 terabytes of data that the whole humankind produces within 1 day. And you know what? It's not that much data. We can process it. And now think about another aspect. People just don't use that many words. So let's say that on average a person uses 10,000 words. It's like totally off, out of the blue sky. I don't know what the number is actually. But I guess that 10,000 words is like a reasonable assumption. How many, another important part. People talk in patterns, right? How many patterns can be composed out of 1 trillion words? Oh, sorry, 10,000 words. What I'm trying to say, not too many at all. So that's essentially our finding. So let me introduce the actual task. So we are talking about categorizing utterances or very short pieces of text. We need to do multi-labeled classification, such that we can say that this piece talks about 2 topics or something like that. And we also need to have a reject option saying that I just have no idea what this piece text is all about. So if every utterance is like, say, 10 words or something like that, then it's actually not that much data, and most of the signal is sitting in a few phrases, say noun phrases or something like that. So what we are proposing here is that extract those phrases, common phrases, categorize them by topic manually, and you will have a classification of all the language of all the people in the universe. And so here is an example, say a question: how many presents have you got to buy yet? So what we do, we remove stop words, we end up with the phrase buy presents, and if it's talking about something to buy and presents, we would categorize into the shopping category. So the most important question, how many phrases we will have to categorize manually? And what we're trying to say is not that many. Let's see, naively, let's say that we have 10,000 words. How many bigrams, groups of 2 words, can we compose of 10,000 words? Like 100 million, right? You cannot categorize 100 million data instances. It's too many. But what's important is that the language doesn't allow you to have all those phrases. Many of them will be too rare to even deal with, right? You don't need to categorize a phrase that just doesn't happen in the language. Or it happens like once. It doesn't matter. So our main finding is that out of 10,000 words, you can build less than 1 million common phrases. And as I covered in the first portion of this talk, you can apply mechanical Turk, spend a little bit of money, and finish classification of all the language of the world within a month of work. Isn't it fascinating? And I'm not exaggerating. So like I am exaggerating a little bit. I'm talking about 2020, right? So it's like in 8 years from now, but still, I think that it's doable. And we actually did something like that with a data set of a smaller size, but we actually showed that it's possible. So how do we count all those common phrases? We use Web 1T data, and that's the data that Google released a few years ago. It's a sample of a language of 1 trillion words. 1 trillion words is a big number, so we can have a very decent sample of the language, especially if we are looking for phrases that are common enough in the language. So I did like quite a lot of pre-processing of this data. I definitely ignored all the stop words because they are not helping for the categorization task. So like if you have a phrase, all words from the dictionary, I just extracted 2 words, dictionary words here. Okay. And that's the resulting data set. You know, not that many phrases that even can be considered as your input. And now what I'm trying to say here is that if we define the notion of a common phrase properly, then we actually can address this problem. We need to have this definition. And what I'm saying is that our words, every words that we're using are distributed as a power law, right? We will have many words that are very common and a lot of words that are rare. Let's take 10,000 words here. Let's find out which word is the least common on that set of 10,000 words. And let's compute all the phrases from these 10,000 words that are at least as common as the data set the word data set that we started with. So I'm trying to say that I look only into phrases that are as common as the words from which this data set was created. And all we need to say, like we have n words in our data set, how many phrases will we have composed of those words? And it's not that many. So we have like a few graphs here. I guess I need to wrap up very soon because, like, you know, I'll go more and more into that topic because you guys probably see that I'm pretty excited about it. But so one of the experiments that we did, we tried to extract all the most common phrases and see how many words you use to build the most common phrases, and then from these words create even more phrases and try to figure out the dependency between the size of the word dictionary and the size of the phrases that you can build from those words. And it turns out that this distribution is actually, the graph is exponential, but the exponent is very small. It's like less than 1.3. And for all practical cases, we're going to like 16,000 initial words here. You end up with less than 500,000 phrases that you actually need to label. And here we propose a little bit more realistic example. In the first example, words were kind of, the initial set of words was very artificial. And in this one, we start with words that are kind of topical. They discuss similar things. And we try to figure out how many phrases we can create from those words. So we end up with something that is getting closer to 1 million, but the dependency is no longer exponential, so it's a linear dependency. So you add more words, and the number of phrases, common phrases that you are adding is actually growing up linearly. And I think that it's actually kind of changes our attitude towards the language, right? So like we just don't have that many phrases that we are using on a daily basis. Once we have identified them, we actually can categorize them pretty much manually because we're not talking about a big data set. Let's say that we'll go to extreme. OK, let's have 2 million phrases in our data set. It will take us 2 months of work, right? Something like that. So that's what I wanted to talk about. Basically, I have many more slides on that topic. We implemented this system for categorizing job titles on LinkedIn, where every job title is a short document like that. And you know, it works in production and earns a little bit of money for the company. And details in this paper of KDD 2011 that we presented last year. Yeah, I guess I'll stop over here, and probably the last slide that I'll show is from my previous presentation, because that looks more beautiful. Thank you, guys. Yes, yes. So this one is actually on my personal website, yeah. Questions?
When you talk about the parallelization where fault tolerance is an issue, is there any difference in the kinds of machine learning algorithms that you would choose, that some that are more or less sensitive to failure?
Wow, that's a great question. I don't have an answer because it's like it's pretty deep. So I would probably, I would definitely make choices of the algorithm based on a problem at hand. And I haven't thought about the robustness and fault tolerance for that. I would basically, I would try to overcome the fault tolerance problem in a systems aspect, but I would still use the algorithm that works best for the particular task that you have in hand. I can give you an example. Say if you have, like, you know, if your data is more like visual or it has the geometry, I would use SVMs because it's like a geometric type of classifier. And if you have like a lot of text data, I would probably use boosted decision trees because they work really good at text, something like that. But it's a very valid question. It's like I need to think about it.
Do you have any studies comparing the percentage of overhead of the distributed schemes, messaging versus this, in terms of the data size? Even if you're using message passing at a certain size, you still need temporary queues on just stored messaging.
Right, and basically, so that's essentially one of the big chunk of whatever we're covering in the book. So you have the computational complexity and you have a communication complexity. And once you are working with a data set of that huge size, you actually really need to be careful about the communication complexity. And we asked our chapter contributors to produce data on how complex the communication is for particular methods that they're talking about. Not all of them did that because, you know, like you can ask, you can dream, but many people actually did do that, and it's covered in the book, and it's a very valid point that you definitely need to take into consideration once you parallelize machine learning algorithms. Sure, they're all my friends, personal friends. So yeah, so the question was about GraphLab. GraphLab is an open source tool that CMU folks are promoting and they're building. It's actually built mostly for matrix factorization. For tasks like collaborative filtering is really easy on GraphLab. So Joey Gonzalez, the guy who is the main developer on GraphLab, actually contributed a chapter to the book, and like, you know, and Carlos Gestrian definitely, who is the professor who in his lab, GraphLab is being developed. So I think that they started with the notion of a GraphLab after we stopped already accepting chapters, but still their team is on the book, and it's a very exciting project of how to parallelize loopy belief propagation.
As we deal with more you are projecting the amount of data that we are dealing with,
Yeah.
and how it will be widespread all over the world, energy complexity might be a more important criteria than, say, computation or communication.
You know what? Also, it's a great question. And to be honest, I think that once we are getting there, we might have different things to worry about. So what I'm trying to say is like that. So like if we are talking about millions of machines that process a lot of data, how much energy they consume is a very important problem. And once we connect it with machine learning, out of the sudden we have a very strange observation. Once you're talking about a data set of that unbelievable size, first, it's really hard to build like a very heavy algorithm that processes it. And even a simple algorithm is pretty difficult. So out of the sudden, all the problems that you're dealing with is definitely systems problems, not machine learning problems. Once you know how to parallelize, once you know how to run on a cluster of a few million machines, then you know what machine learning is just not in your focus any longer. And that's why what I'm trying to say here is that we definitely concentrated on machine learning, and which essentially means that we, right now at least, we don't think about data of trillions of instances. We don't think about tens of millions of machines. It's just not really practical. And you know what? In 10 years at least from now, someone will have to produce a new book. And probably even in 5 years from now, because it's like how fast it's growing, it's just pretty much unbelievable. Guys, what will we do in 5 years? It scares me. And I am serious. It's too much data out there.
Hi, can you make a comment on doing parallel in batch learning in a huge amount of data as compared to online learning, which you have data continuous streaming in, where you have already a model, but you actually overlay some of these new data?
Yeah, yeah. So we have a chapter on online learning. It covers it. It's only one chapter. So in many of our chapters, it is batch learning when all your data is actually given to you a priori. But we have a chapter that comes from John Langford, who essentially is a big expert on online learning. And this, what is something that you won't find in the book, actually, is that he wrote this chapter literally like pretty much when we were closing the deadline of the camera ready. So it's very timely. It's like the very last finding in the area. It's very important to take this into consideration, and we are very happy to actually have this work in the book, because John was working like crazy last few months to produce those results. Please take a look into the book, and you will find information about that.
One comment. There's a science fiction book called Accelerando that sounds an awful lot like your predictions.
You know what? I'm also always happy to hear that. It means that I'm not crazy.
Or there's correlating crazy.
Well, then it's already mainstream, right?
Yeah.
Thank you, guys. Thank you very much.